So trigonometric identities are kind of where you start to move into a little bit more advanced trigonometry. They still end up on things like the ACT sometimes, but they're absolutely essential for doing stuff in calculus and other higher level math classes. So we're just going to taste them just a little bit this year. Okay, so first I'm going to write down the trigonometric identity tools that you have. I think about identities as like things I can grab down in my pocket, tools I can pick out like a hammer, a chisel, a speed square, anything like that. They're tools that you can use to attack a problem, to change it into something simpler, okay? I think we know a couple of the trigonometric identities that we're going to use in this section already. So let me see if you guys can tell me a couple of the reciprocal identities. So you can, if you want to remember some names to help yourself be oriented, you know, there's lots of families of identities. There's actually an infinite number of these. In the back of any calculus or trigonometry book, pre-calculus book, something like that, usually there's about 50 to 70 of them listed. Does that mean my best calculus students have all 70 memorized? No. Well, some of them might, because they're crazy. It's possible, but yeah, I think the main answer is no. I mean, like, do I have all of those things memorized in the back of the book? I am a teacher, so like probably most of them, but like I don't think I learned them that way. I really have about 10 memorized, and that's it. And really, when you're looking at this first set of them, you're probably going to want to think about 5. The other ones should just kind of come naturally. They should flow, if you will, from kind of stuff that you already know. So I think the reciprocal identities are not things you need to memorize. You should already know them. Let's see. So the reciprocal identities. So there's one for secant, there's one for cosecant, there's one for cotangent. Maybe we should start with cotangent. That's the easiest one to remember. Like on your unit circle, cotangent. How'd you do cotangent? You thought about tangent, right? And you did what with the tangent, Kyle?
Moved over right.
You're thinking the graph. I'm talking unit circle when we very first mentioned these. You flip it, right? Well, you're allowed to flip it because cotangent's really just the same thing as dividing by tangent, taking 1 and dividing by tangent. And there's another identity which says tangent is, guess what? 1 over cotangent. So they reciprocate both ways. That comes from flipping. So this should be stuff you already kind of know. So secant was 1 over what then? It goes with cosine. Cosecant goes with sine. In fact, it's 1 divided by sine. So I'm hoping that you already have these down, kind of. I never really wrote them like this, but we've been using them like this. Well, what this says, an identity, means for any angle it works. That means if I plug 45 degrees in here, and I plug it in here, it's going to be the same. If I plug 30 degrees here and here, it's going to be the same. If I plug 12 degrees here and here, it's going to be the same. Identities are identities for any angle. Any angle fits them. Does that make sense, guys? Anything fits them, really. If this is like 2 theta, you could put 2 theta here and here, and it'd work. If this was like 4 Cookie Monsters, and you put them here, and you put them here, it would still work. It works for any possible thing you can put inside. Okay? So those are things I think we already know. Let me remind you, I think you've seen this one as well. Here's a nice derivation, which any person who knows trigonometry should be able to do in order to explain to their friends how to do some basic trig or anything like that. It's the most important derivation in trigonometry. I think I did it with you once. Let's see if you guys remember. So if you have like the unit circle, and you just kind of draw a random angle. This works for any angle. I'm going to draw an acute angle. And it would work if I went 120 degrees or 200 degrees or whatever, right? So if I draw that angle, and we think about a point on the edge, something like xy, how could we rewrite xy? You guys remind me? Yeah, one of them's the sine and one of them's the cosine. How would that go? X is cosine? Okay, I'm going to use red. So x is cosine, and y is sine. Now, why was that again? Let's remind ourselves of why that was. It's because if you looked at this triangle, how far is this? It's x, very nice. How far is this? y, but then we said, all right, so if you take a ratio and you go cosine of theta, you do adjacent, what's the hypotenuse on this guy? It's 1 for the unit circle, right? And that's what says x is cosine. And then we went sine of theta is opposite hypotenuse. So that says y is sine. That's how we came up with this to begin with. You guys got it from memorization. Very important little diagram to remember how that kind of works, because that's where that came from, right? So this gives us another one of our identities. It's not really a reciprocal identity. I'm just going to put it down here. So if sine is y and cosine is x, what's that mean about tangent? Yeah, and what have you guys been using to do tangent on the unit circle? Tangent is opposite over adjacent, and for us, y was sine and x was cosine. That's an identity. Any angle, if you take its tangent, it's the same thing as doing sine of it over cosine of it. I think we've seen that one. So likewise, cotangent is cosine over sine if you flip it. Or if you look there and do cotangent, it works. Okay, that I think we've already done. We haven't used it a lot yet, though, so now you're going to start really using this a lot. From this same diagram, you get a whole nother family of identities. Here's their name. Get some of this out of the way. So we said we could label this as x and y, or you could label it as sine and cosine. I'm going to label it like that. Because what kind of triangle is this?
Right triangle.
Nice. So if it's a right triangle, don't all right triangles have to obey Pythagorean theorem? You know, like a squared plus b squared equals c squared. So like, do it with this triangle. A squared. Well, I've been doing my identities in black. I guess I'll keep them in black here. I'll keep them in black. A squared plus b squared equals c squared. 1 squared's 1. Whole other new family of identities. If you take the cosine of any angle, you square it. You take the sine of it, that same angle, you square that, you add it together, you'll get 1 every time. It all comes from the same little diagram. Now, if you looked in your book right now, you'd see there's not just one Pythagorean identity. There's 3. How many does this guy remember? Just that one. And I don't even really have that memorized. I know this argument, so it's not a memorization thing for me anymore. It's like, oh, it comes from here, see what happens, you know? And there's 2 other ones. I swear, I still mess these up to this day. If I try to write them down from memory, there's 2 other versions of this. There's more than 2, actually. But if you know this one, you can get the others. Because there's also one for cosecant squareds, and that's kind of what I remember. I'm like, yeah, there's also one for secant squared if you want there to be. There's also one for cosecant squared. What is it exactly? I always screw it up, unless I go back to here. And I say, if I wanted this to have a cosecant squared in it, what could I divide by? If I want cosecant to be in there, won't I want to divide by sine? Because 1 over sine is cosecant. Do something to one side of equals. You have to do it over here too, right? So here's the main identity. 2 other versions are cosecant squared theta equals, what's this? Careful, look over there carefully, guys. Cosine over sine is cotangent. Plane cotangent? Cotangent squared. And what's this? 1. There's another Pythagorean identity. I always screw up like where the 1 goes, you know what I mean? Stuff like that. So if I ever need these for sure, I write this down and I divide by the thing I want to get what I need. There's another one too. There's one with secant squared. So I remember this. I remember like there's identities for all those squared things. That's about all. That's about all you need. And I'm like, okay, so if I divide it by sine squared, I might as well try dividing by cosine squared. You do it to one side, you gotta do it everywhere. Yeah, let's see what happens. What's on this side now? Secant squared. That's 1. So I know our cosine is tangent squared. There's another Pythagorean identity. So I only have one of them memorized. You can do what you want. You can try to memorize these. That's great. Totally works for lots of people. I bet you'll forget by next year, though. And I'm guessing you probably need them in your next class if you go on to more advanced math. So, I mean, you can learn it over again. Really, I just remember this. Write down Pythagoras and go. Your choice. Okay. So there's one other little family of identities we're going to look at, and then we'll just start using them for things. So these are the, I don't know, they have a pretty boring name, the negative angle identities. There's really 6, but your problems are going to ask you to figure out the other 3. So what if you put a negative angle into your cosine, into your tangent, etc.? What happens? Once again, you can totally just memorize this, but then you'll forget. See, I've had classes with engineers multiple times where you need to know these, pull them out of your pocket and use them, you know what I mean? And a lot of the time they don't. And that's because I know they, if they learned them the first time, learned them by straight memorization instead of learning them organically. So, where do these come from other than just, you know, memorizing? What kind of transformation is this? Let's think about cosine. I think it's easiest. Cosine. Let's think about the picture of cosine, a graph. Yeah? Think about what cosine looks like in your head. And then what does putting a negative inside do to it? Which way does it flip it? Does it flip it down? Or flip it this way? It flips it this way, yeah. Because it's inside, right? Inside stuff's horizontal. Think about cosine in your head for a second. Clearly, if you're watching the video, do the same thing. What happens if you take the cosine curve and do this? It stays the same. You guys should have that in your head by now, what cosine looks like in general, right? Cosine starts up, it ends up, it looks like this, kind of, yeah? So if you go and finish another period over here, it looks like that. What happens if you take that shape and go like this and, you know, you actually drew the shape well? It copies onto itself. So what's that mean the cosine of negative theta is? It's plain old cosine. So the weak way to remember this is be like, okay, when cosine chomps on negative angles, they go away. That'll work for you, but there's no meaning behind it. That's why. Because that means reflect it that way. Yeah? Okay, so think about the same thing with sine. I'll give you guys a second in your head and see if anybody can tell me what the identity is. Think about what sine does when you go like this. 1 second. You got an idea, Michael? I'll ask. Is it going to stay the same? No. So what is this? What's the answer? Anybody have a guess? You think cosecant?
Sorry, that's wrong. What am I trying to think?
It's negative sign. Let's think about why. So thinking about the picture, if you're having trouble remembering it in your head, sign looks like this, right? I'm going to go backwards 1 period. Think about taking that shape and flipping it sideways, reflecting it across the y-axis, as Rachel was saying. This hump will become this one, right? This one will become this one will become this one will become this one. It'll make a perfect braid. But the red curve's clearly not the blue curve, right? It's totally different. So the question is, how do you make the red curve become the blue curve? What can you do with it? If you now take the red curve and do this, what happens? It'll match. It'll flip onto the blue curve. Well, how do you do this with transformations? So, the fast way to remember this, if you want to remember it for a short time period, is to say, sine, when it choose on negative angles, they come out in front. Yeah? But that's the reason why, or that's one reason why. There's other ways to derive this too using more advanced math, but it's my favorite easy one. So what do you guys think about tangent? Let's see if we can do tangent without even drawing it. Think about what tangent looks like if you do this with it. Does it copy onto itself? No, but it's like perfectly reversed, isn't it? So yeah, if you do the other reverse, it'll work again. So tangent is like sine. That's because these guys are both what we call odd functions. They have origin symmetry. This guy's an even function. He just becomes the same if you flip him that way. Those are called even and odd functions. Okay, so those are the identities we're working with. Let's do some simplifying problems. Let's do some actual problems now.